Okay, Earth science time. Today we are talking about the birth of Earth. Birth, isn't that cute? Birth of Earth. I have deliberately chosen birth. I mean, that gives it a little hardcore, what someone might call a realist might say that personifies the formation of Earth too much. I'm not afraid of calling it the birth, and I think even to call it the creation of Earth would be appropriate and nice. And one of the things that alludes to, even if I say words like "in the beginning," that there's an allusion there that kind of gets at a type of controversy that some people experience in here or somewhere in between when we start talking about things like this. But I'm going to present this to you in a way that I hope you will find is based on evidence and still allows for you to have room to, what's the verb I'm looking for? To harbor, maybe, to feel belief of a supernatural version. No, not version. That's not the right way to use. A supernatural facet of this. Do you get what I'm talking about? So Earth was born about 4.5 giga-annum, 4.5 giga-annum. What evidence is there for that? We'll talk about that in a second. And probably over the course of the next approximately half a billion years, which is 500 million years, it was forming. It was in the process of formation. So what was there before? That's an interesting question, both philosophically, metaphysically, and physically. What was there before there was Earth? Right. This is Earth science, and so if we're talking about geology, the study of the planet Earth, maybe we are now talking about proto-geology, or the study of the beginnings of planet Earth, and that interfaces with what other study. Well, there's a lot of answers to that question, but primarily, what other part of science that we're going to be talking about? So, like in the last lesson, we talked about the hydrogeology, right? The interface between the hydrosphere and the geosphere that was groundwater. And now we're kind of talking about not just geology, but what other science? Astrology. Definitely not. Be very careful, because this word astronomy, which is from the Greek for to name the stars, is, we say, the study of the stars. We really use it as the study of space in general, of outer space, of space that doesn't, although I don't like that very much because it pretends like Earth is not part of space. Y'all are part of space. You are a space critter because you live in space. But also we want to be careful of astrology. All the other ones went in an ology, but because of that's older than actual science. You might say, I would say this is very generous. You might call that a pseudoscience. That's very generous. It's not weird rock people. It's star signs. It's like, hey girl, what's your sign? I'm a Gemini, obviously. Obviously, I'm a Gemini. And Kesslin absolutely does give total Aries vibes. And so maybe I'm not saying that's not real, but whether it's real or not, that's kind of what I was talking about back here too. Whether it's real or not, it's not science, okay? And that's not bad necessarily. It's just not science. That's not what we talk about. No, get that out of here, because there's not evidence for it. There's not physical evidence for it. So we're talking here about physical evidence. You want to talk to me about if there is evidence beyond the physical? We can talk about that some other time. But in science, we talk about physical evidence, and that's where we come up with these numbers. To put an even finer point on it, someone's going to say, but what about 4,000 years? Right now, you get that illusion probably. And the answer is, physical evidence says no. Is it possible? Sure, science is not about proving things, but physical evidence suggests this number as for the beginning of the creation of Earth, and this number for approximately how long it took before it was solidified. So we talk about the interface between geology, the study of planet Earth, and astronomy, the study of space, and that we sometimes might call astrophysics, or I think I've heard the word astrogeology before, and those would just, oh no, it's exogeology. And these refer to the way that this process occurs, the way that planets in general, especially exogeology, means planets other than planet Earth, form. So the formation of planets. So we're talking primarily about the birth of Earth, but because Earth is a planet, we're talking in general about the formation of solar systems. Well, tell me what a solar system is.
It's a bunch of bodies, and they're all in the system.
Group of, everything's interconnected, but interconnected celestial bodies. Why does your boy have to put things like celestial bodies? We're just getting definition within definition. Why this? Why not just say planets? It's not just planets. There's star or stars. Star. Within a solar system, there's star or stars. There are planets, certainly. There are dwarf planets, which we categorize differently from planets at Neil deGrasse Tyson. I was about to say comments are disabled for this video. They're not. I re-enabled comments. If you want to leave comments at Neil deGrasse Tyson, someone can do that. Stars, planets, dwarf planets, what else? What other things are within a solar system? What else makes up the system? Remember, systems and system models are one of our CCCs, our cross-cutting concepts that pervade all of science. What other things make up the system of interconnected components of a solar system? There are celestial bodies.
Bunch of dirt.
Yeah, you already said asteroids. I'm going to write that one. Dust is, for some reason, seems slightly more professional than just calling it dirt. Gas. Remember, when we talked about soil and sediments, we talked about how dirt is a nonsense word. Dirt is a garbage can word for everything that we want to call dirt. Like, the definition of dirt is, I want to call this dirt. And so that's what we call it. Anyway, there's dust, there's gas. What else? There's a couple others that I want to talk about. Come on, there's a big one, kind of in here-ish. Moons. You're right, moons, satellites. Those words we kind of use interchangeably in earth science. Okay, well, I think that's good. These are the most of the bodies that exist in that we consider to be. Well, what about your human body? Should we put that on there? No, guess what? You are part of a planet. Baby girl, one of the things I'm trying to teach you in this class is that you are not separate from planet Earth. You are part of planet Earth. You are part of planet. You are Earth. That's not wrong. Just like my boy Alan Watts says, it's just like an apple tree apples. Right? There are apples coming out of an apple tree. Planet Earth peoples. There are people coming out of planet Earth. You're not a separate thing that landed, although we are going to talk about impacts. You didn't land in a rocket ship like Superman on planet Earth from somewhere else. You are part of planet Earth. So, yeah, especially in the case of Justice, that may not be true. It seems false. Actually, in the same way that Kessa was giving off Ares vibes, Justice does give big super ET alien vibes. And so... And Eminem, like if a rapper came and landed on planet Earth and got that haircut. Okay, so how did this all start? Well, physical evidence suggests, again, is there a metaphysical or spiritual answer? Not only probably, but I would say yes. However, we're talking about the physical answer. How did this get started? Well, step one, what?
I don't want to answer.
Yeah, you do. Answer. Answer. Any answer. You might be wrong, but any answer. What's step one?
Step one for what? Tree.
Yeah. Dylan just picks a noun and says it as loud as he can. Okay, step one, gravity. I like that. Let's put that. Gravity does what? Gravity is a noun. What does it do?
It clumps.
Okay, yeah, clumps, pulls. I'm going to use the science word coalesces.
What does that mean?
Coalesce means like a bunch of, it's related to the word coalition, which is where there's a bunch of small groups come together to make one bigger group. Coalesce means a bunch of small stuff comes together to make one big stuff. In a way, when your mom sweeps the bakery, she's coalescing all of the dust. Not dirt. That's a garbage word. That could be anything. But no, she's doing it to the dirt. Yeah, she's getting all the dirt from all over and coalescing it. Okay, so gravity does these things. Making a what?
Proto-planet or something like that. I don't know.
So that's a little bit. So we got now. So we have gravity, which is it is itself a force, right? Force. It is. There's an energy field that permeates the entire universe called the gravitational field, and that provides energy for things like clumping, pulling, and coalescing together. A cloud. A nebula is the Latin word for cloud. What evidence? This is really important because if we're going to say it's based on physical evidence, then what is the physical evidence? What is the physical evidence that this can happen? What is the physical evidence that this can happen?
Because it's happening.
Because it happens.
Because it is still happening today. It doesn't happen, well, it does still happen in a sense here in this solar system, but we can see it in other solar systems. We can see this forming. We can see other nebulae, and some of those nebulae are planetary nebulae, where a new star has or is forming, and we can see this happening. We can see it happening through telescopes. So that's one piece of evidence, a very good piece of evidence. Okay, so now we have a nebula, and over time that nebula does what?
It gets closer together.
Yeah, several parts of it, based on where the most of the mass is, coalesce again, or we might even say accretes. So the accretion, I'm actually going to change that to accretion, making that verb into a noun. Someone's asking the question, what's that mean? Accretion is like when a cloud comes together to... No, for some reason I would think that's the sound it makes. But yeah, it clumps. It's coalescing again, but now it's held together. Each individual object is held together under its own, in this case, gravity. So kind of like your mom might coalesce all the dirt into a dirt pile. She then might accrete it into a dirt ball. No one does this, but you might accrete it into a dirt ball and then just yeet that ball out, right? But that would be the process of accretion, where now the cloud, what was a cloud of gas and dust, has become a more or less solid object. And at some point in this process, I'm going to put a squiggly with 4 because it might have happened somewhere else, but stellar fusion begins. Stellar means referring to a star. So
it's the fusion of stars.
not the fusion of stars one to the other, but the fusion of hydrogen atoms, which is what most of the universe is made of. This cloud, this nebula, would have been mostly the element hydrogen in its diatomic state. And so then when these hydrogens smoosh together fast enough under the energy of what? Gravity. When they smoosh together fast enough, they fuse together to form helium, and that is stellar fusion. That releases an enormous amount of energy. That's what a star does. In fact, that's what the universe does. 99 point whatever percent of the mass in space, maybe not dark mass and dark energy, who knows, that's not really what we're talking about, but 99% of the normal mass in space is undergoing stellar fusion. It's held up in stars. And then we get, let's go to 6, whatever, protoplanets. These kind of smallish lumps that we call protoplanets, and then those collide to become planets, big planets that we have today. So the driving force for all of this, again, maybe, is there a spiritual answer? That's not what science is about. Not yes and not no, but that's not what science is about. But the physical evidence suggests the primary driving energy for this is the force of gravity. Now, the sun has been in the middle. Just on accident, why would the sun be in the middle?
It's big.
Yeah, because that's where most of the mass is. So as the cloud, the nebula, the protoplanetary nebula condenses, most of the mass ends up in the sun. I'm going to, I think, pretty safely say 99%. There's no way this is showing up on video, but what I've got here in yellow is a picture of the sun drawn by an idiot with a line pointing to it that says 99%. Most of the mass is held up in the sun. And then you will know the order of the planets. I'm going to do these in black so you can actually see them.
Red, orange.
Nope, the order of the planets is not red, orange, yellow, green, blue, purple, purple. It is, in fact, first of all, I'm going to teach you these little symbols too because I like them and I want you to like them too. What's the first planet as we go out from the sun? Mercury. So Mercury, there's a symbol for Mercury, which is like the female symbol but with little horns on it. That's also a symbol in alchemy for the element Mercury. From there out, we have Venus, which is, you know the symbol for Venus, it's the same as the female symbol. And then the next one is It's Earth. Earth has a cross in it. There's a couple of different ideas about why that is. One of them is that it represents the prime meridian and the equator, but the symbol for Earth is just a circle with a cross in it. Next, Mars, which is the male symbol. I'm going to have to start doing them like this. War, because war. The next one is
Jupiter.
But hey, guess what's out here?
Asteroid belt.
Asteroid belt. Jupiter's symbol
To get more stupider.
is to get more stupider. It looks kind of like a fancy 4 or a fancy 2. It comes from the Greek letter. It's not the Greek letter zeta, but it comes from that, which is the first letter of the word Zeus, because Zeus and Jupiter are synonymous in those pagan religions. Next. Saturn looks like a fancy H with a cross through it. Represents Saturn, the god of agriculture. Next.
Uranus.
Let's try to pronounce it Uranus, which is, I think it's the Mars symbol, but with a dot in it. And then finally, the final planet, Neptune, which is the symbol of a trident to represent Neptune. Also, the sun has a symbol, which is just a circle with a dot in it. The moon has a symbol. Yeah, it does.
Yeah.
I don't remember. That one I've forgotten. Could it just be like a crescent moon? It very well might be. I'm probably wrong. Several of these asteroids have symbols too, but no, there is no Pluto. It does have its symbol, but that's a dwarf planet because it hasn't cleared its orbit, meaning that the mass of the other objects in its orbit is more than its mass if you add them all together. But that was kind of a neat little exercise, and that was to remind you of the order of the planets and to introduce you to these symbols that I really like, and they don't really have any meaning other than that. Well, of course they do, but in this lesson they don't have any meaning other than that. But these planets here that I have coincidentally drawn like that, we call what? That group of planets are called the
Cool ones.
The cool ones, no? So we'll start with these ones. What are these ones all called? The gas giants.
Oh.
Gas giants. Sometimes we call these two, Uranus and Neptune, the ice giants. But as a group, these four are called the gas giants. What are these four called then? Terrestrial planets.
Yeah.
Terrestrial is yet another word meaning referring to Earth, but this refers to that they are rocky. It refers to Earth in the sense that you might say that your dog was digging in the earth, like the lowercase e, the material Earth. So terrestrial meaning they're made of the substance Earth. So these ones are rocky and relatively dense. These ones, and also relatively small. These ones are gassy, relatively not dense, light you might say, and very, very large. Why? Is it a coincidence that the four, I'll give you a hint, the answer to that question is almost always no. Is it a coincidence that the four inner planets are rocky and the four outer planets are gassy?
No.
It isn't a coincidence. It's because of this, Justice will remember this, it's because of the centripetal force. As a cloud of gas spins, the heavier things will coalesce towards the middle. Well, especially, that's actually not true in the centripetal force. The heavier things will coalesce to the outside. But when the mass of the sun is gravitationally pulling it there, and the gas that was at the center of this cloud is all pulled into the sun, these ones don't have as much gas to be made out of. And so as the protoplanetary nebula spins, the denser stuff ends up in the middle. This is an important phenomenon that we will, again, address when we talk about the Earth. And it's actually kind of opposed to the centripetal force, because in the centripetal force, the heavier stuff moves out from the circle, but because of gravity, it's pulled in. And in this case, gravity wins. The heavier stuff is pulled inward, and the gas giants are made out of the leftover gas that is away from the sun that wasn't made into that. Now, what other evidence is there for these time frames specifically, and this process in general? The best one probably is that we see this happen in other solar systems. So we can, again, use uniformitarianism. We can, I'm just going to start spelling it however I want. As my old friend and mentor, Dr. Lighty, called it, trading location for time. We can't go back in time, so we trade a location for that. We look at another location where this is happening, uniformitarianism. What other evidence exists for this time frame and that these processes occurred?
Because it's happening.
Yeah, I just said that one. So what else? Yep. Let's call it radiometric dating. Yep, exactly. And really, if you look at your book, you'll see this. Actually, it would have been really romantic if we did birth of the Earth first. Like, it's Earth science. If we talk about the birth of Earth first, that would have been romantic. But the museum at Fort Robinson closed, and so I wanted to go there before they did that. So radiometric dating is the idea that as radioactive materials, primarily in rocks, we usually find them in rocks, radiometric materials decay, we can measure that rate of decay, and that will tell us how long it takes for half of the parent isotope to become a daughter isotope, which we call a half-life. And we do this of Earth's rocks, although not very often. And why? Yeah. Earth's surface is not just a surface, although that's what we can get at, is very energetic, and so it's constantly being reformed. Plate tectonics, erosion, other surface processes make it so this is kind of difficult to use here on Earth. Not impossible, but it's difficult to use for the oldest rocks because they frankly mostly don't exist anymore. What else do we, before I go on, we do use it though on space rocks. So either by going to them or when they come to us, if we do this on an asteroid or a comet or whatever, we almost always get dates in this range. Because and the inference is that those bodies, those minor celestial bodies, were forming at the same time as the rest of this, but they cooled down a lot faster because they're very small, and they stayed that way because they don't have surface processes. Erosion doesn't happen on asteroids because there's not an atmosphere. There's not plate tectonics. It's already cold. And so almost always when we date them, we get this date somewhere within this range, from 4.5 to 4 billion years old. So that's actually a major piece of evidence, is that all the space rocks, except for the ones we find on Earth, are about this old. What other evidence is there? This one will be kind of ancillary to the process. What's the main piece of evidence that we use for dating the past in Earth science? L. There is an L.
There's an L. There's an L. No, by an A.
There's no A.
Oh. U.
Fossils. So, again, that's not direct evidence because there weren't fossils. There were very shortly after this. We do find some very, very old fossils. But of microorganisms, which are hard to find fossils of, and it's hard to find rocks of this age anyway, and there wasn't life at the beginning. But by seeing the progression, if we look backwards in time, from present back through the fossil record, we see as we go back in time, we see the fossils getting simpler and simpler. Eventually, it's only single-celled organisms, and the oldest ones of those we date to about 3.5 billion years old. So if already there was life on planet Earth at least 3.5 billion years ago, that's another piece of evidence that this time frame is roughly right. And an important thing, and this is lovely when this happens in science, it almost always does, when these three pieces of evidence, radiometric dating primarily of asteroids, fossil evidence, and other solar systems forming that we can see, they don't have to agree, and they do. And that tells us that we're probably right about these ages. I think in a nutshell, I would say that's how the physical way that the Earth and its system formed. But that's not all we're going to talk about today, so hold on to your little shorts. Do you have questions before we move on, though, about the physical formation of Earth and its solar system? It sounds like you don't, and so I'm going to assume that that's true. Now, because of the influence, I'm going to change color so that you know we've shifted gears. Because of the influence of gravity, we're going to keep that one up there. I'm going to erase everything else. I might keep up my, I already started erasing that, so I'm going to keep that. And I'm going to erase all of this and this. But I think I'm going to keep this little diagram here. Because of gravity is the driving force of motion in the solar system as well. Planetary motion, or we might call it satellite motion, because this is true of minor satellites orbiting around a planet. That is, this is going to be true for the planets orbiting the sun. It's true for other planets orbiting other stars. It's true for moons orbiting planets. And there are 3 laws of it. These are Kepler's laws of planetary motion. There are 3 of them. The first is called the law of ellipses. And what this tells us is that the planetary orbits, any orbit, is necessarily an ellipse. If you've ever learned from the simulation Kerbal Space Program, Justice, you will remember this. It is so that one of the lovely things about that simulation that it teaches us is it is so difficult to the point of impossibility to get a perfectly circular orbit. Nothing is perfect. Nothing in nature is what we would call mathematically perfect. It's there. So there's a kind of perfection that you're like squinting at stuff and you're like, yeah, that's perfect in its own way. But mathematical perfection is an almost unheard of rarity in anything, even in the heavenly orbits, in the celestial realm, that is the heavens themselves. The ancient Greeks, and because of them early Roman and Middle Ages philosophers wanted them to be perfect, and so they invented things like epicycles. But they're just not. It's just so hard for them to be perfect because there are so many variables. Perfection and simplicity go hand in hand, and because in reality there are so many things going on, it's very difficult for it to be perfect. And so the law of ellipses tells us that all planetary orbits are not perfect circles, although obviously that's not a perfect circle. Pretend it is. They're actually ellipses. And that's not an oval. It's the conic section related to a circle that has, instead of one focus, it has 2 foci. And so a line drawn between these 2 foci, which is the plural of focus, will be equidistant from both of them. Is that the right word? At Eric.Snitley, ask Eric.Snitley about how ellipse is actually defined. But basically, it is like a circle, but instead of being based around one single point, the center, it is based around 2 points, the foci. And so all the planetary orbits have as one of their focuses, that's not a real word, as one of their foci, the sun. So for a planetary orbit, one focus is the sun, and then the orbit forms around that and the other focus. And so for Mercury, one of the foci of Mercury's orbit is the sun, and the other one is outside of, well, not necessarily outside the sun, but outside the center of the sun. So all of the orbits are ellipses, and the degree to which they are non-circular is called their eccentricity. Have you ever heard of something being eccentric? Like you probably have an eccentric uncle who like doesn't wear pants in public or something like that's. I mean, eccentric is a nice word. It's not very nice, but it's a nice word for weird. Like your uncle who, it's usually an uncle, isn't it? I mean, he's probably been divorced a couple of times. He's got the weird shirts. He eats food that no one else eats. He's eccentric, right? There are probably those who would say, I'm eccentric. Everyone has a little bit of eccentricity, just like every orbit has a little bit of eccentricity, meaning it's not entirely circular. It's non-circular. And the degree to which it's not circular is called eccentricity. And 0 eccentricity or eccentricity means it's a circle, and 1 means it's a hyperbola. It doesn't even close. The orbit it's not even really an orbit as such. It just zoop, goes off, okay? So it goes from 0 to 1, and the closer to 1 it is, the more, so it's like, this would be 0, a perfect circle. Obviously I drew a perfect circle. And then maybe this is 0.5, and then 0.99 might be like that, where the sun is here, here, here. Okay, so that's the law of ellipses. The next one is called, and they're all related, but this one's directly related. The last one is called the law of equal areas. And this governs how quickly a planet moves in its orbit. So the definition of a circular orbit, which again doesn't exist, is that it would be moving, Justice will remember this also from Kerbal Space Program, that the faster an object is moving, the closer it is to its orbiting body. At what we call apoapsis, which is the nearest an object gets to the body it's orbiting, it is moving as fast as it possibly can be. So close equals fast, far equals slow. Basically, that's like an idiot's version of the law of equal areas. Kepler's law of equal areas says that in the same amount of time, a satellite will always sweep out an equal area. So if it's very eccentric, it'll sweep out this area when it's very close, and when it's far away, only this area. So it's the same area. Like if we measured, it's supposed to be the same area. If we measured how much red is taking up here, we would have the same amount as the red taking up here. But because this one's short and fat, it's going zoom around there. And because this one's long and skinny, it takes that same amount of time, right? He says the same amount of time to govern equal area. It's farther away, and so it takes the same amount of time to go a much shorter distance. So basically, close to the thing it's orbiting, fast, far away, slow. Apoapsis, the nearest it gets, fast. Periapsis, the farthest away it gets, slow. In a circle, I started the sentence and never finished it. All of that was a parenthesis. In a circle, it would be going the same speed all the time. That's one of the reasons why in our concepts, it's so hard, impossible to get a circular orbit, is because to go that same speed the whole time under the influence of gravity is incredibly hard. It would be governing two variables at once and being in balance perfectly. And then finally, we have, I think this is the most beautiful name in all of science probably, but the law of harmonies. Isn't that beautiful? The law of harmonies. And what this amounts to is basically, I'll make an idiot version again. Mathematically, it's this. I'm not calling mathematicians idiots, but this is the simplified version. T squared is proportional to r cubed, is the math of it. And in idiots' terms, the farther away planets take longer in their orbits. Capital T is period. The period is how long something takes. And r is radius, how far away it is from the body it's orbiting. So the square of the period is proportional to the cube of the radius. The farther away an object is, the longer it takes to orbit. And these three things together are Kepler's laws of planetary motion that are observably true. That means every solar system we see, and within our own solar system, and even the microcosmic solar systems of like a planet and its moons, these hold true for all of them. Every orbit is an ellipse, God bless you. Every object moves faster when it's closer to its orbiting body and slower when it's farther away. And the farther away it gets, the longer it takes to orbit. Fundamentally true for everything. And back to the first thing we talked about, these also govern how solar systems are formed. That planetary nebula, that cloud that exists before a solar system does, is elliptical in shape. Things that are nearer to the object move faster, and things that are nearer to the center move faster, and things that are farther move slower, and things that are farther away take longer to orbit. Do you have questions, do you feel like, about Kepler's laws? You'll have more information from your text, and as you're working on your assignments, you'll hopefully learn a little bit more about the details of this, but do you have questions about this in general? I knew you wouldn't. Bye!